In this lecture, we're going to talk about what we call the numerical methods or the approximating solutions for differential equations. Especially, we talk about the first order differential equation in this. So what we try to do are numerical methods. Numerical methods. Numerical methods. Or sometimes what we call approximating solutions. Approximating. So approximating solutions. Now the question is why we want to do this. So there should be a reason for that. So let's talk about this idea. So what I'm going to call let's look at what we call the non-elementary integrals. Non-elementary so there are some special integrals. For example, let's look at this integral. So e to the negative x squared dx. So this is I should say the most important integral in science, like pretty much in all sciences, but unfortunately you cannot integrate this one. So the most important integral you cannot integrate. So this integral is what we call the Gauss integral. Gauss integral. Gauss integral, and later you can see that this is gonna simply related to the error function. Error function. So the question is, you cannot integrate this one. So that means you can integrate. This means, like, you know, you cannot express the solution. You cannot express the integral as an elementary function. But you know, if you want to find the definite integral, for example, you can see if you have negative infinity to infinity e to the negative x squared dx. If you need this one you can integrate. There are techniques to do that, and once you integrate, you can see that you're going to get square root of pi. So if you get square root of pi, then what's going to happen? What you can do is you can divide by square root of pi both sides, like that, and then you're gonna get equal to 1. So what is 1? So this is the reason why we use this in this is what we normally call in the other ways the bell curve in statistics. So if you look at the graph of the bell curve, that means that's a function for that. So if you graph it, so this is what you get. So that's the graph of this function, and what this says that the area under the curve is 1. So that is the reason why this is used in statistics or probability, because this area is simply going to be 1. So the area equal to 1. Area equals 1. So, and then in other terms, what it says that the total area from negative infinity to positive infinity is 1. So this is what we normally call the normal distribution. The normal distribution. So the normal distribution, or the Gaussian distribution, because he is the one who came up with the idea. Gaussian distribution. So what I want to tell you, so the most important integral you cannot integrate. So what we normally do is we're going to use what we call the approximations. We're going to approximate this, and then we're going to use those approximations to for calculations. But there are techniques that you can approximate as accurate as you want. So that means, let's say you need something accurate to if there's error has to be less than 10 to the negative 20, something like that, but you can do it. So there are techniques to do that. So that means you can approximate the solution as accurate as you want. So after we like find the accurate solutions, what we can do, we can use them, and then that's pretty good enough. So this is one integral. So let's talk about what other things out there. So I'm going to call this in number 1. So there are some other integrals also. These are very useful, but unfortunately you can integrate. So the second one I'm going to call the Fresnel integral. So that means sine x squared dx, or cosine x squared dx, cosine x squared dx. So these are what we call Fresnel integrals. Fresnel integral. These are useful in optics, actually physics. So Fresnel integral. Fresnel integral. This is used in physics. So that's the second class. So this is also you can integrate directly. And then the third one, what we call elliptic integrals. Elliptic integrals. So there are a lot, but this is just few. The next one is what we call elliptic integral. So it is 1 minus x to the 4 square root dx. So you can integrate any of them and get the closed form solutions for that. So this is what we call the elliptic integral. Elliptic integral. Elliptic integral. And also as the fourth one, I'm going to give you what we call the Dirichlet integral. So that is sine x over x dx. This also some people call the sinc function. So this is called the sinc function. This part is called the sinc function. So this is equals to sinc. So we write sinc x dx, and this is also another integral that you cannot integrate. So this is actually also called the Dirichlet integral. Dirichlet integral. So this is called the Dirichlet integral. Dirichlet integral. So these are just few integrals that you cannot integrate, or in other words, you cannot write the answer in closed form. So that means, and then they are like everywhere pretty much. So the Dirichlet integral is like in engineering, you can find this integral. Elliptic integral also appear in engineering applications, and then the Fresnel integrals appears in physics and optics. And then the first integral, Gaussian integral, is pretty much everywhere. So because that's a normal distribution, that's the most common distribution. So but unfortunately you can integrate this one. So that means there's a need. So this says that there's a need for approximating solutions. So let's go to that idea. So that means so what we see that cannot find exact solutions, or what we call the closed form. Solutions to most common integrals. And then why we are worried about the integral, and we know that when you have a differential equations, the solution come as an integral. So that's why we worry about whether we can integrate or not. So what we're trying to do now is so this says that we need approximations. So need approximations. Need approximations, or what we normally call numerical solutions. Numerical solutions, approximations, or numerical solutions, in other words. So let's look at the problem at hand. So we trying to find solution for this problem. So what's the problem? Y prime equal a function of x and y, along with you are given this information. You are given a point. You know there's one point in the curve on the path. So that means if you look at the graph, this is the situation. So so you know the directional field because you know the slope curves. So you know the directional is everywhere, and also you know one point on the path. So you know one point on the path, one point on the path, and you also know the directional fields everywhere. So you know the directional fields everywhere. Okay, so you know the directional fields everywhere. That's the directional field. So the question is, given this information, can you find the solution? So that's the goal. So given this information, can you find the solution? So there are several answers. So yes, we can find the solution, and then what we're going to learn in this one is what we call the most common one, or the easiest one, called Euler's method. So we can learn about the Euler's method. That's the easiest. Euler's like oil. Euler's method. Euler's method. Easiest. Okay. Easiest. Not very accurate. Not very accurate. You know, when something is really easy, you don't get good results. So that's kind of common thing. Good. And then so who is Euler actually? Euler is like one of the most influential mathematician. He is actually so he's called Leonhard Euler. So Leonhard Euler in I think 1707 to 1783, if I'm right. Actually, the things that he discovered was like, you know, he made a lot of contributions to mathematics. For example, the number e in mathematics is his introduction, and then the complex I. He is the one who came up with the idea I, and the sigma notation is one of his discovery, and the functional notation f, like, you know, we write f for functional fx. That's his idea. And then also what we call the Euler's identity, ei theta. We can discuss that later. Like these are like just few things that he came up with: e, I, sigma, f, ei theta, all of them. So he's the author of them. Good. So again, the Euler's method is the easiest one, or what we call the most simplest method to solve a differential equation. So we can write it again like that. So the easiest or the most simplest method to solve a differential equation. Okay. Good. So, and then there are other methods as well. We can also talk about some of the, like, how to improve this idea to, like, certain things. For example, two other ideas that we can discuss is what we call the improved Euler method. Improved, or sometimes what we call the modified Euler method. And also we can talk about the most common and most important one, what we call the Runge-Kutta method. Runge-Kutta. So that's the most common one. So this is like we use like pretty much everywhere in most engineering and other applications. The Runge-Kutta method, that's very, very accurate, and we can talk about all three today. So let's start with the first one, what is called Euler method, and how it works. So the Euler method, Euler's method. So how it works? So this is like very simple idea. We just use like college algebra for this one. So let's say you have a graph. So this is your function. So I'm going to call it t and y, two variables. So then what information we know? We know the information at the yeah, let's call it x. It's easy. I don't want to confuse. Okay, so so what information we have? We know that dy by dx, which is equal to f xy, we know that, and we also know that y x naught at x naught, it is equals to y naught. So that means we know that at x naught it is y naught. We know those information, and then so we know that information, and we know like the slope field or the directional a field everywhere. Okay, like if you pick any point, we know what is the slope at that point. We know that. Now what we're trying to do, and then let's say this is your actual curve that you don't know how to. Okay, so let's say, so this is your actual curve. Okay, that's your curve that we don't know, that's we are trying to find. So what we're gonna do, we're gonna draw the tangential line at that point that we know. So because we know this point, we know this point. So I mean, what we can do, we can draw the tangential line at that point. So let's draw tangential line. So that's a tangential line. Now what we can do is we can find this equation of this tangential line. So so what's the slope of this curve? So this curve has a slope. The slope is simply given by this function. So at this point, the slope that you can say, so I'm going to say m. So which is simply, you just plug in that x naught y naught to the function. That means slope is simply f x naught y naught. So that means we know the slope and we know the point. So we can use the slope point form. So we can use the slope point form to find the equation of this curve. So we use the slope point form. Slope point form. So if you use the slope point form, what is that? It is y minus y naught equal the slope times x minus x naught. So if you plug in here, so you're gonna get the slope is f x naught y naught. That's a slope. We just plug in that to the equation dy by dx. So you get the slope here, and then we have x minus x naught. And then if you move the terms around, so you can write this one as y equal y naught. If you move the y naught to the other side, plus, and then we have the slope here, so it is f x naught y naught, and then x minus x naught. Now, so that's the equation of the tangent line. That's the equation of the tangent line. Okay, the equation of this line is y equal y naught plus f x naught y naught and times x minus x naught. Now what we can do, we can evaluate this at any point. So let's say you know another point, like let's say this is your other point. Now what you can do, you can evaluate that one at another point, and then you can approximate the solution to the curve at that. So this so that's the approximate value. So you can approximate the value using this line. Okay, so that means your approximated value is gonna be as a y1. You just simply calculate using this one. So that's the first approximation to the exact value, but you can see that there's an error. So that's the error you're gonna get. So you're gonna get this much error. How to reduce the error? If you make the gap smaller, you can see that if you make the gap smaller, the gap between x0 and x1, if you make it smaller, you can reduce the error. But there are some issues with that, because when you try to make it small, we don't know whether you can handle that. Like especially we're gonna calculate this one using computers, but when you try to use a computer, there's a smallest number that you can handle in a computer. So that means there are some limits to those things. Okay, now so we use the first approximation. Now the idea is to use that new point as the starting point and do it again. So what we're gonna do now, we do the same thing. We draw a line which is parallel. So we're gonna calculate because we know the slope field, we know the slopes everywhere. Since we know the slopes everywhere, we can find the new slope at that point. So we're gonna find the new slope at that point and draw the new line. So the new line is, you're gonna start at, we're gonna find this new slope, and then new slope coming from the slope field. So it may not be exactly equal to the slope at the curve, but it's just the slope at that point. So we're going to draw the new line. So it may not be the tangent line anymore. So we're going to calculate the new slope, because we don't know the exact curve. So if you know the exact curve, we don't want to do anything. So we don't know the exact curve. That means the only thing we can do is we can find the slope at that point. So we find the slope at that point, and then we draw the new line. So we can start with that point as the starting point and find the slope. Do the same thing again. So your new curve going to be like this. So that's the new one. We start with that point, and then do the same thing again. We're going to find the equation of this line. So this is going to be very easy. Compare from the previous one, we can guess this one. So let's see how the things gonna work now. So and then we can find the y1. So we let's finish the next one. So we can see at x equal x1, at x equal x1 we have y1 equal y0 plus f x0 y0 x1 minus x0. So this is the first approximation. This is the first approximation. The first approximation. The first approximation. So now what we can do, we can use the new approximated value. Okay, so we can say now we use x1 y1 as the starting point, and do it again. Okay, so that's the idea. So we can use this one as the new starting point. So you can see that it's just a problem with a new starting point. So we can pretty much do the exact same thing, because we can find the slope, because we can plug in that point to the equation, differential equation, and we can find the slope. So if you plug in here, you can see you're gonna get the slope. So that is the one focusing on, but that point is not there anymore. But we still have the same differential equation. Okay, so we're gonna use that, and then we can see it's a very simple argument, very similar argument, and then your new equation gonna be just you need to replace the x0, all the x0 by x naught by 1. So that means the equation of this new curve gonna be simply y equal y1 plus f x1 y1, we know both of them, and then here it's going to be x minus x1 because you just transform all the knots to 1. Okay? So you can see, so what you did was you simply transform zeros to 1. So and then you can see in the next step you're going to transfer 1 to 2. So just keep doing it. Now since we know the new tangent line, we can approximate the value again at the new value. So what we're going to say, let's say you want to find the value at let's say x2. So then this is the new value. So that means so your approximate value is this. So if you cannot integrate, I mean, this is the only thing we can do. We cannot do anything, you know, because we can integrate the function. So we can only approximate, and you can see that. So there's one thing you notice, there's a huge error now. See the error? So that's the error. So you can see it's getting larger and larger. So that's why this method is not that good, because when you go further away from the starting point, that error can get, it's not 100% sure because we don't know how the curve behave at this point. Maybe the curve is very close to that one, but that we don't know, no guarantee for that. So but in general the error can get larger and larger because this is the exact solution. That's the exact solution or the actual solution. Okay, that's the exact one that we don't know. Okay, we don't know about this one, so we don't know. So but error can get large. Okay, so that's the idea. So that means in general we can write a solution. So if you know the previous step, then we can write the next step. But there are certain things that we can do to make the calculation easier. Yeah, you can see that in every time you try to kind of pick different gaps for the x values. What we can do is we can make those gaps easier, like equal. All of them are equal. So when they are all equal, then you can simplify this formula. So so that means we can write what we can do is we can make the gaps the same. So let's talk about that idea. So let's say so we can say we can use equal intervals, equal gaps, we can say equal gaps. And call it h. So we can call that gap h. So that means if we know the gap is h, then we can see, so this is what's going to happen now. So we're going to start with x0 and we go equal gaps. So it's x1, x2, x3, like that. So that's the gap. They are all equal. So that means we can write a formula now. So you can see in general we can write this one as so x I plus 1 is simply the previous one plus h. So in other words, if you start with the x0, you need to add I many h. So that's kind of gonna give you the formula for the x values. Those are the x values, and then we can write a general formula. So what's the general formula going to be? So we can say in general your y I plus 1 step is simply equals to yi plus f xi yi times xi plus 1 minus xi, but you know that this gap is simply h. So that means your formula you can write as simply yi plus you find the h times you find the slope at the previous step, yi xi yi. So so this is gonna be the so then you can write a formula. So so let's write a few other things also. So we can say I'm gonna write a formula. So we'll say we divide, let's write it like that, we divide the interval, we divide the interval x naught x into equal subintervals, into equal subintervals, equal subintervals with gaps h which is given by this is simply the gap is x I plus 1 minus xi. So how you get that? It is simply let's say you have an interval from a to b, so it's simply normally like b minus a over n. N is the number of subintervals that you need. So here n is the number of subintervals, the number of sub interval. So you can decide how many subintervals you need, but more the better. So more the better, more the better. That's the kind of idea. Okay, so that's how you get the gap. So it is, the gap is how you normally get b minus a over n. B, a are the two intervals, the starting value and the ending value, and it is how many you need. Okay, so with this information, then we can write the formula like this. So we can say I'm going to say the Euler's method. Okay, so Euler method is simply so you're going to calculate so you can use n or I or something like that, but I want to, like, go with standard notations. So let's write it like this. So let's say your x n plus 1 is simply x n plus h, and then your y n plus 1, the next step is simply y n plus h times f x n y n. So you can use n or you can use I, it doesn't really matter. So this is gonna work for n starting with 0, 1, 2, like that, depending on how many points you need. So this is the Euler's method. So it's very simple. So you can see that just knowing the derivative and the starting point, you can repeatedly calculate the next one or the next approximation. Okay, so a very simple formula. And also you can write this one, you can, if you like, you can write it like this. So you can write this same thing again as this x naught plus n many h, so n h. So you can write it like that. So this is gonna give you the, knowing the nth step, this is gonna give you the n plus first step. Okay, so this is the Euler's method. Simple, very simple idea. So now what we can do is let's look at a real problem. So let's just try to get the idea from this example. So let's look at the first example, just like a basic idea. let's say you know dy by dt equal ft y, and you also know y t naught equal y naught. That is starting point. So let's see how we can do this problem. So let's say let t naught, the starting value, equal 1 and y1 equal y naught. Find y3. So let's say you have this kind of problem. So you need to find y3. So you are not given how many steps you want. So let's say n equal 1000. You're going to go with 1000 steps. More the better. Okay? 1000 steps. So what the situation looks like now? So let's look at the corresponding graph just to get the idea. So we know the starting value t naught, which is equal to 1, and y naught, you know that also. So this is y and this is t. So what we're going to do, we're going to go with equal gaps, and then we know that the n equal, so let's do the calculation now. So we know that n equal 1000. This is normally given, and then what we need to do is we need to find the h, the gap, which is b minus a over n, the number of steps. So in this case b is 3, a is 1 starting, and then number of steps is 1000. So if you simplify, you're going to get 0.002. So that means you can calculate your first t1 value. T1 value should be t naught plus h. You can add one gap. So that means 1 plus a 0.002. So that means 1.002. Okay, so that's the first one. So that's t1. So that's the t1. And then you can do the same thing, and then we calculate t2. So what is t2? T2 is t1 plus h. So that means it's going to be, you add one more, so it's going to be 1.004. So you can just keep doing it. So that means your ti going to be t naught plus ih. Good. So we're going to go with the equal gaps. So this is the h gap, and then we have t2 gap. And why we have equal gaps? Just to make the calculation simple. Okay? You don't have to, but in practice we don't do that. We're going to go with different gaps, but let's discuss that later. So we do that until we end up with 3. So the question is, if you want to go to 3, how many steps you want to do? At what step you're going to get it? So let's write few steps. So we know the y naught value, that we know as something given. Then we calculate y1. So what is y1? Y1 is y naught plus h times f x naught y naught. Now you know y naught, and you also know x naught, and we know the function, we know the h value, so we know everything. That means we simply know this value. So if you write further, if you substitute little further, you can see y naught we know, and the h is, we know that it is 0.002, and then we can calculate this value because we know the slope field. So that means we know this value. So that means we simply know the y1 value, and we also know the actually not x naught, we use t naught. So I'm going to write this as t, this is t, this is t. Great. T naught, and this is also t naught. Okay, so we know all of these. So we're going to get the value. Now what we're going to do, we're going to go to the next level. So we're going to calculate y2. So let's calculate y2. which is y1 plus h times f, the next value, so it is t1 y1, and then you can see that we know all the values, so we're gonna get y1 that we know from the previous step, and then this is 0.002, and in the function we know t1 value. What is t1? T1 is 1.002, and we also know the y1 value from the previous step, so that means we know y2. So just keep doing it. So how, at what step you're gonna get y3? So we need y3, so you're looking for y3. At what step you're gonna get y3? So y3 is simply y 1000, right? But to get y 1000, because in the 1000th step you're gonna get that, so that means to get y 1000, what we need to do, you need y 999 plus h, we know it's still the same, and then here f, it is 2 point, because it's just one step behind, it's a 2.998, and then y 999. So that's the value. So at that value you're gonna get the value you are looking for. So you can see that this is just a simple for loop calculation in a program. Okay, so you can just use the we don't do the hand calculation. Okay, use a simple for loop. For loop, use a simple for loop to calculate this. Okay, so this is like very simple idea. Just use a simple for loop, and then you can see that you're gonna get this value very quickly. So the calculation not that bad, but what you need to do is we need to understand, how things gonna go. And then also so you can see it's not a difficult calculation. So we always stay one step behind. Okay, so if you need the 10th one, we need to calculate the 9th step, then you're gonna get the 10th value, because we can use a tangent line. Okay, so it's like a fishing rod, so you're gonna get the next one. Yeah, okay, so and then there are also things like we use to find the error. So the question is how to find the error, how to measure the efficiency of this one. So let's talk about that next. So we say how to find, how to measure efficiency. Actually, how to measure accuracy, not the efficiency, accuracy. How to measure accuracy. So we can use certain things there. So we can use what we call the absolute error. Absolute error. So what's absolute error? So absolute error means the one, what we're trying to do is the exact value minus the approximation. Approximate value. And you can see that this may not be available in practice, because if you know the exact value, what we need the approximation. But these are just to evaluate whether the technique is good, but in practice we don't know the exact value. This is just for like theoretical computations. And the next one is what we do is a relative error. Relative error. So what's a relative error? So relative error means so we're gonna do same thing first, so exact minus the approximation, and you're going to divide this one by the absolute value of the exact value. To the absolute value, because we don't need the negative value. So that's what we call the relative error. And then also we have a third one, what we call the percentage error. That's the most common one we use, the percentage error. Percentage error. So what's the percentage error? We calculate the same thing as the previous step, and then we multiply by 100. So we're going to get the exact value minus the approximation. Take the absolute value, divide by the exact value, absolute value, and times the 100%. So we're going to calculate the percentage value. So that's what we call the percentage error. So so there are three things. Those are three things that we normally use, and we can also use the ratio between the previous error and the current error. That's another one we do. Like we're gonna measure the what's the error in the previous step, what's the error in the new step. So because that has to go, if it's getting smaller and smaller, that's a good one. Okay, and then let's talk about the how to write the pseudo code for this kind of algorithm. So I'm gonna give you the pseudo code for the algorithm. The pseudo code. Pseudocode for the Euler's method. Pseudocode for the Euler's method. So we're going to start with the first one. We can define the function. So different programs have different ways to do it. So we can define the function. In MATLAB, we can use the @ operator to do that. In Python, we use the back arrow for that. That's in Python. Okay, number 2, we can input the values. So we can input the values t0 and y0. Those two are given. And then number 3, we can input the step size h, or the number of steps. And then in number 4, what we're going to do is we're going to write a simple for loop for that. So we're going to say for j going from 1 to n, we're going to do what we can do. The first one, we're going to calculate the slope at the y0 value, and then we're going to find the equation. We're going to find the first approximation. It is y0 plus m times h. And then we can update the t value, t1 equal t0. We can update the t value, and then we have the y1 and t1. So we're going to print them. So let's do that. So step D, print t1 and y1, and then in the last step we can update the t0 to t1 and y0 to y1. We can update them, okay, or replace. or replace. Good. And then this is gonna end the for loop. So this is the pseudocode for the Euler's method. So as the next one, what we can do is let's do a real problem here. So so let's do this one. So the example. So let's say for the initial value problem, y prime plus 2y equal 2 minus e to the minus 4t along with y0 equal 1. I'm going to call this star for future reference. And first, how to find the solution for this one? For this one, you can actually find the exact solution. What is the technique? And if you look at this one, you can see that this is the first order linear, so that means you can use the integrating factor method. Okay, so yeah, so let's say use Euler's method. Use Euler's method with step size h equal 0.1 with step size h equal 0.1 to approximate the value of the solution at h equal 0.1 to approximate, or you can to find the approximate value, to find the approximate values of the solution at t equal 0.1, 0.2, 0.3, 0.4 and 0.5. And then compare them to the exact value. Compare them to the exact value. Exact values of the solution. Okay, so let's see how we can. So this is a kind of typical problem that you're gonna get, so you're gonna get a differential equation, you're gonna get a starting point, and then they're gonna tell you either h value or the number of points. Normally the h value, because we just try to find out few values, so we're gonna get the h value, and then they're gonna evaluate it at few points. The independent variable can be t, x, it doesn't really matter. Okay, so the answer, and then you can first integrate this function and get the solution. So I'm going to write it here. So the solution to the IVP is, so this is an easy one. Okay, so it is yt. If you find it, you're going to end up getting 1 plus 1/2 e to the minus 4t. So this is a good practice with this is the case. Okay, so you can check that, and e to the minus 2t. So this is what you should get. So that's the exact solution. Now what we're going to do, we can use the Euler's method, but we know that to use the Euler's method, you have to write the differential equation as y prime equal. That means you have to remove the 2y term to the other side. So let's do that. Let's move the 2y term. So we can say to use the Euler's method. Okay, rewrite star as y prime equal 2 minus e to the minus 4t minus 2y. So I'm going to call this function fty. Okay, so you're going to redefine the function as fty. You can see that it's a function of two variables, t and y. And then so we can say, so let fty equal 2 minus e to the negative 4t minus 2y. And then also we know that t naught equal 0, that's given. And then also we know that the y0 equal 1, that's also given. And then also, just to make the calculation easier, sometimes we use like a different notation. What's the other notation is, we can write ft naught y naught as simply f naught, and then we can write ft1 y1 as f1. So we can just keep using that because it's gonna make the calculation a little bit easier. Okay, so let's do the calculation now. So what we want to do, we need to find the slope, and then we're gonna plug in it there. So let's start with the values. So we can do f naught. F naught is simply f t naught y naught. So that means t naught is 0 and the y naught is 1. So we're going to plug in those two values in the function. So it's 2 minus e to the minus 4 0 minus 2 1. So if you calculate this, you end up getting negative 1. That's f naught. Now we can calculate the y naught, y1, the next value. So it is simply y naught plus f hf naught according to the notation. That means it is 1 plus h is 0.1, f naught is negative 1. If you simplify, you end up getting 0.9. So that's the f1 value. And then we can also calculate t1 value. T1 is simply h we know, and then we can add that, then we can get the t1 value. So you can say, and t1 is simply t naught plus h. So that's the t1 value, which is 0.1. Okay, so you know the t1 y1. Then we can calculate the next step. So at the next step, we can calculate f1, which is f 0.1, 0.9, then 2 minus e minus 4.1 minus 2 times 0.9, because these two coming from the previous step, because we already calculated these two. So so this is t1 and this is y1. Good. So if you simplify this, you end up getting negative 0.47032. Depending on how accurate it is, it would be better to have like write few extra decimals in a step like that. So and then we can calculate the y2 now. So y2 is, according to the formula, it is y1 plus hf1. So we know all of them now. So it is 0.9 plus h is 0.1 times negative 0.7032. So if you simplify, you end up getting 0.85296, like that. So you can see, so that's the second approximation. Okay, so we have this is the first approximation. So repeating this process, we're gonna have f2, which is equal to negative 0.1 negative 155.264, and the corresponding y value is y3, which is 0.837441, like that. And then we can do f3, which is 0.0239922. You're gonna get the y4 value as 0.83 9833, and then y4 which is 0.118335. so the y5 equal 0.851677. okay, so that's the value you are looking for, the fifth approximation. Using the Euler's method, so it's not that difficult. So what you need to do is, so you want to find the slope and then use the recurrence relation. So let's go back and talk about what we did. Good. Yeah, so this is a recurrence relation. So what do you need to do? You need to calculate the x value, and then using the x0 and y0 value at each step you get the next one. So you can see it's a very simple formula, and we repeatedly used it to calculate the next step. Okay, good. Okay, so now, so let's talk about whether we can improve this. So good. So we had that. Good. So let's talk about how to improve this technique. So the next one is we can talk about how to improve. How to improve. So the one of the things that gonna come to our mind is we're gonna use small h. But the problem is when you try to think about to use the small h, so there are some practical issues now. So what are the practical issues? What are the difficulties that we're going to come across? So there are a few difficulties in such a situation. So if you try to use a smaller h, that means you need more steps. Okay, so small h means many steps, many calculations. So that means the issue is what we call the computational time. So that's a big one, computational time. So this can be like scary at times. I can remember when I was a graduate student, I had a program running for more than a year just to calculate what we call a dimension. So you have to be very careful with those kind of situations. So the computational time can be really an issue for some of the calculations, because in practice we cannot wait that much. Like for example, let's say you want to predict the weather. So if you have a weather model and if you want to know what is the temperature tomorrow at 2 p.m., you cannot wait a week to find that number. We need to do it really fast and get the results as soon as possible. So that means the computational time can be really a big issue. So that's the first one. So if you try to go to smaller h, you need many calculations, so it's going to come up with a computational error. So that means there is a limit how far you can go. And then the next one is what we normally call the what we can say applicability. So for example, the next one is what we call the round off error. Because we try to use them in a computer, but the computer has the smallest number it can handle. what we normally call the machine epsilon. So there's a what we call the machine epsilon. Sorry. We normally write EM. So the machine epsilon is the smallest number the machine can handle. So if you try to go more smaller than that, the machine gonna consider this as 0. So if we try to use numbers smaller than epsilon m, the machine may consider them as 0. So that's the problem. So once it's consider them as 0, everything is wrong after that. That's what we call round off error. So you can round to something and then it's gonna create issues. Okay, so you have to be careful with that also. And the next one is what we call the stability. The third one is the stability. So what's the stability is, do we know that whether, you know, like let's say you're gonna go with a smaller edge, or you're gonna get more number of steps, and the question is, do we know that even if we doing that, can we really reach the actual solution? So that's what we call the stability. So there are certain problems, no matter how small your edge gonna be or how many steps you're gonna try, it never reach the actual solution. So those are the situations like what we call stability. The algorithm does not give you the one you expected. Okay, so this is the question. The question whether we get the solution even if we have smaller edge and many calculations. So that's the what we call the stability issue. So sometimes that can be because there are certain problems, even though you consider very small edge or many calculations, it never reached the solution. So that means we need to find new techniques. Okay, because of that we need to kind of come up with better algorithms. Okay, so because of that need better methods. Okay, so one of the such technique is what we call the improved Euler method. So let's talk about that. So what is the improved Euler? So what we're gonna do, like, you know, we're gonna make the algorithm a little bit better than what we had before. So let's talk about the that idea. Okay, the improved Euler. That's the second technique. Improved Euler method. Sometimes this is also called the modified Euler method, improved Euler method. So this is the idea. So what we can do, so let's look at the graph. So so this is the x value and the y value. So let's say you have a graph, and this is starting point, as before. So we have let's say xi step, this is the yi step, xi yi step. So then we try to find the next step. So what we're trying to do is we're going to do a similar thing as before. We're going to do the slope first. So that's a slope, so we can look at the slope, and then so I'm going to call that slope is the ki, ith slope. And then what we can do, as before, we're going to find the slope at that point. So that's the I plus first from the next point. That's the same thing we did before. So we're going to find the slope at that point. It's a new one. So we're going to find the slope at that. So it is a ki plus 1, because we know the point here. So now what we're going to do, we're going to draw a line parallel to that at this. So we're going to draw a line this parallel to this. So so this is the line that we're talking about. So we can draw a line parallel to this, parallel to that line. And then what we're going to do, we actually going to use the average slope of these two for the next one. So you can see when you look at the average slope, you can see it is in between, so that's very close to the the next one. So we can use the average slope. So that's the average slope, and use that value as the next approximation. You can see this value is much closer to the actual curve. That's the idea. So we can use this one as the next approximation. This one. So we can use this one. So this is I plus 1. In the Euler's method, what we used was this one. So this is the Euler's method. Euler method used this one. Okay, that's what the Euler method used. So the improved Euler used the bottom one. The bottom one, because you can see that is much closer to the actual answer. Okay, so that's the idea. It's a very simple idea. So the slope wise is the same slope as ki plus 1. So what we do is we use the average slope. We use the average slope in the improved Euler method. Is the average slope, and then we're gonna reach when that gonna go to the so the rest is the same. So you see, use the same edge. So those are the same, but we use the average slope now. Okay. This is also normally called the predictor corrector method, because you see that you predict the new slope here. So that's a predictor. You predict this, and then you're going to correct it. So this is a corrector. So that's a corrector. So this one is the corrector. So you're going to correct that. So these are called predictor corrector method. Predictor corrector method. Predictor corrector method. Good. Okay, so let's do the calculation. So what we need is we need a slope, which is the average slope. Average slope. So that means it is 1/2. We can take the average between the two slopes, ki and the ki plus 1. Those are the two average two slopes. One at xi, one at xi plus 1. So that means if you plug in that to the formula, it's 1/2. So f, we're gonna go with xi yi. That's the first slope. How to find the second slope? Second slope, we know that f, the value is xi plus 1, and then what is the y value? Y value coming from the previous line. Okay, so right, y value coming from the previous line. So that means it is still yi plus h k1. Yi plus h k1. So it's the same thing. So it's simply coming from the previous line, previous slope. So that's the part we need to remember. the y value you're gonna is coming from the previous one. Okay? So it's a yi plus hki. So that is the second one, and then that's it. So those are the two slopes. So this is the ki slope, this is the ki plus 1 slope, the two slopes. Yeah, so then we can write the algorithm for this problem. So it looks like this. So let's write it. So we have, we can say x I plus 1 equal xi plus h, or x naught plus ih, no difference. And then we're going to calculate two slopes. We're going to calculate k1 slope, which is simply f xi yi, and we're going to calculate k2 slope, which is the slope using the new line. So it is, here it is xi plus h, the next step, and then here it is yi plus h k1 coming from the previous step. So you can see that's a k1 you already calculated, so you're going to put that there, and then your new yi plus 1 is simply yi plus the average of the two slopes. So h over 2 k1 plus k2. So this is the what we call the improved Euler method. So you can take the average of two slopes. So I'm going to give you a problem for you to try, so you can do this as an exercise. So this exercise, so let's say use improved Euler. Use improved Euler method to approximate y at 1.54. Let's say y prime equal 2xy along with y1 equal 1 with h, let's say 0.1. So you need to do 5 steps. So you can see that it's not it's very similar to what we do in every time h is 0.1. So you're going to jump like 0.1 every time. So then that's going to give you the xi value. So you're going to start with x naught, y naught. X naught is you can say is 1, and then y naught is 1, and then we're going to plug in there. So you're going to first calculate a k1, just plug in x naught, y naught, so to the function, so you're going to get the k1 value. And then also you're going to plug, after you find the k1, then go to k2 is f xi plus h, you're going to add the h, and then you're going to calculate yi, that means the y naught plus h that we know times k1 come on the previous step. So we're going to plug in those two and then evaluate, and then after you get those two answers, you're going to plug into the bottom equation. That's, you take the average of the two. Okay, once you take the average of the two, it's going to calculate the next step. And then after you know the next step, you know, so if you start with x naught, y naught, you're going to get x1, y1, and then use x1, y1 to calculate x2, y2. Okay, like that. So yeah, so I'm going to write it here, some steps. So what we do, we're going to start with x naught, which is 1, y naught, which is also 1. We can use those two to calculate x1, y1. Okay, after you calculate x1, y1 using the formula, then use those two to calculate x2, y2. So keep doing it until you get 1.5. That means the fifth step, because you want to start with 1, so you have to do fifth step. In the fifth step, you're going to get the answer. So the answer for this problem is answer is, how much you get? You're going to get 3.4 3.4509. See whether you're gonna get something close to that. 3.4509. So that's the answer. Okay, so this is the next one. That's what we call the improved Euler method. Then what we're gonna do is we're gonna go to the most important method. The most important one is what we normally call the Runge-Kutta method. So let's talk about that now. That's the next one, the Runge-Kutta method. So let's go to Runge-Kutta method. Runge-Kutta. Or sometimes what we call the RK, and we also call RK4 because this is what we normally call the fourth order Runge-Kutta. So let's write it. So we're gonna call this is the fourth order Runge-Kutta. That's the actual name, fourth order Runge-Kutta. So that's how we call this RK4, fourth order Runge-Kutta. Okay, so let's look at the idea. I'm just gonna give you the formula for this one and how we do it. So as before, we're gonna do the similar thing here. We're gonna start with x0 value and then gonna go each equal gaps. So x0, x1, x2, like that. So that's the gap, the same gap h. So the formula are, so we're gonna the problem is exactly the same. So we have y prime, which is f xy along with y x0 equal y1 y0. So we have those two information, and then how to find the approximate solution. So so that means we're gonna repeatedly calculate. So we're gonna say for I equal 0, 1, 2, like that. So we can repeatedly calculate your xi plus 1 step. The next step is simply xi plus h, or it is x0 plus ih. That's going to give you the next step. Now what we're going to do, we're going to calculate 4 slopes now. So what are those 4 slopes? So we're going to calculate k1 slope first. K1, the first slope, it is exactly the same as before. It is xi yi, that's the first slope. Now what we can do, we're going to calculate a slope at an intermediate step. So what we do is we're going to calculate the slope exactly in the middle. So so let's say we have xi, and that's xi plus 1. So that's the h gap. What we're going to do, we're going to calculate the slope exactly in the middle. So we're going to go halfway in between. So we're going to go halfway in between. Okay, so we're going to go halfway. So that means your equation going to be like this. So we're going to calculate k2. So the k2 is simply f xi plus half h. So you're going to go half h in the x direction. And then we're going to calculate yi plus the same thing, h half k1. K1 comes from the previous step. Now do the same thing. Do k3, which is f xi plus h half. This is yi plus h over 2 k2. K2 coming from the previous step. And then you calculate k4, which is f at the end point. So it is xi plus h, and then yi plus hk, hk3 in this case. So you can see that k1 coming from the previous step, k2 coming from the previous step, k3 coming from the previous step, and then after we calculate those 4, then your new y I plus 1 is simply going to be yi, the old one, plus h over 6 k1, 2 times k2, 2 times k3 plus k4. So that is the formula. You know, this is like little complicated, but it's going to give you excellent result. Okay, that's one of the importance of this one. Looks difficult, but excellent results. And then this one is we use in numerical solvers. Okay, so used in numerical solvers, like even in computers, MATLAB, Python, they use that. A little modified version, but we can talk about that in a minute. So used in numerical solvers. It's very accurate, numerical solvers. Okay, used in numerical solvers. It's in Python, it's in MATLAB and Python. Okay, so use in MATLAB. And also Python. So you can write simple Python code for that. But MATLAB has a built-in function for that, and Python also has a built-in function for that because it's really good. Good. Okay, so let's look at an actual problem. So yeah, so I'm gonna put them in a box. So this is the Runge-Kutta method. Good. So let's look at an example. So use the Runge-Kutta fourth order method. That's that, because there are 4 steps that I call fourth order method. That's not exactly the reason, because it's accurate up to the h to the 4th power, so order of h4 as a fourth order method. We talk about those in numerical analysis classes. Okay, use the Runge-Kutta fourth order method with h equal 0.1 to approximate y 1.5 for the same problem, y prime equal 2xy along with y1 equal 1. Okay, good. So let's see how the calculation gonna follow. So what we can do, we gonna calculate those 4 slopes, and then we can plug in there. Okay, that's how we do it. So let's do that now. So the answer, so we're going to start with the I equals 0. That's the first step. So this is, then you're going to get x1, which is x0 plus h. That means it is 1 plus 0.1. So 1.1, because x0 equal 1, the starting value. So if you draw them, it will be very clear. So that is starting value x0, and then we have h is 0.1, so this is x1, x2, x3, x4 and x5. So every time it is 0.1 gap. So this is equal to 1, so that means you're gonna get 1.5. That's what we are looking for. And then xi is simply x0 plus ih, or in this case 1 plus 1.1 I. Good. So let's do the calculation now. So if you do the calculation, so first we need to do is we're going to calculate k1. So let's calculate k1. So k1 is f x0 y0 according to the formula. So it is 2 x0 y0. If you plug in x0 and y0, y0 equal to 1, x0 equal to 1, so you're going to get 2. 2 times 1 1, you get 2. Now calculate k2. So what is the k2? It is f with the formula x0 plus 1/2 h, which is 0.1, comma y0 plus 1/2 h times k1, which is 2, is coming from the previous step. Good. So if you simplify this a little bit, you're gonna get 2 times the function is 2xy, so it is 1 plus 0.05 times 1 plus 0.1. So if you simplify, you're gonna get 2.31. Okay, so let's do k3. So what is k3? Is f x0 plus half 0.1 comma, we don't need this one, comma y0 plus half 0.1, and we use the previous value. And if you simplify using the formula, you end up getting 2.34255, and that's the value we get from the previous step. And then so if I show you the steps, what happened here is 1 plus 0.05 times, you're gonna get 1 1 plus 0.05 times 2.31. Yeah, so that's how you get it. So you're gonna use the calculator and then multiply the 2, so you're gonna get that. Okay, so k4. So k4 is, again, actually that's easy. K4 is f x0 plus 1 such gap, comma comma y0 plus 1 such gap times the previous number, 2.34255. If you simplify these two, you end up getting 2 times 1.1 here times 1 plus 0.234255, and if you simplify this, you end up getting 2.715361. Okay. So those are the values you're gonna get. Now you're gonna plug in. So therefore we have y1, the next value, which is y0 plus h is 0.1 divided by 6, k1 plus 2k2 plus 2k3 plus k4, which is equals to 1 plus 0.1 over 6. Let's plug in the values. So we have 2 as k1, 2 times 2.31 as the second value, 2 times 2.34255 as the next value, and then 2.715361 as the final value. And then after you simplify, you end up getting 1.2367 as the next approximation. Okay. Now what we can do, now we have the x1 value and the y1 value. We're going to use those two to calculate x2 and y2. Now we use x1 equal 1.1 and y1 equal 1.2336. so it depends on how many decimal places you want. So always go one extra. Okay, if you need to be correct to 3 decimal places, go with 4 decimal places. At the end you can round, don't round at the beginning, well it's going to give wrong values. To find x2 and y2, so we can do the same calculation again using x2 and y2. So we need to calculate the 4 slopes and plug it to the formula. So we can see that in a table. So let's see, so let's do the calculation and see how things gonna work for the next few calculations. So let's see. Okay, so so these are the next few calculations, and this is what we got for this one. So so we got this one as the first value. Now what we can, so we start with 1 and then we calculate this, and then you can see that this is pretty close to the actual value. So that's the actual value. Actually this like up to 4 decimal places they are exactly the same. But if you look at the Euler method, and then we also try to use the improved Euler. If you look at the improved Euler, I mean that's pretty accurate, but if you look at the Euler method, it's like much off from that answer. But you can see improved Euler is a little bit better than the Euler method, but you can see the Runge-Kutta gonna give you the pretty much the exact value at in the first step. Now what we can do is we can repeatedly calculate. We can use that x value and the y value to calculate the next one. So you know repeat it. So that means if you, so this is the y1 value, this is the y0 value, and then we use those to calculate y2. So this is x0 value, it's x1 and x2, x3, x4 and x5 and similarly the corresponding value y0, y1, y2, y3 and y3, y4. So we have y3, y4 and then you have y5. So you can see once you calculate, that's the value you are looking for, and that's the value you get at the 5th step, and you can see that's very close to the actual value. That's the actual value. You can see it is 3.4902, that is 3.4904. so you are only off by 2 of 10,000. So this is like very good. And if you compare this with the Euler method, you can see how off it is. So that's why we don't use the, so this Euler one. So this Euler, and that's Runge-Kutta. So you can see it's very accurate. But you can see the improved Euler is also like a little bit better compared to the Euler method, but Runge-Kutta method gonna get the exact, I mean pretty much the exact same value. Not the exact value, but very close to it. Okay, because it's very accurate. Now the question is, can we improve further? Yes, what we can do is we can make a smaller, or we can have the h value and see what's gonna happen. So if you have the h value, you're gonna get this. So you can see if you have the h value for the same problem, for the Euler, you're gonna get these values. For the Runge-Kutta, you're gonna get these values. So this is for the Euler, this is for the Runge-Kutta, and you can see they are very accurate compared to the values. And then in the table you can see these two are pretty much the same. Okay, So you can see except the last digit, but the other values are exactly the same. So that's why the Runge-Kutta method is used in most of the numerical calculations, because the results we get is excellent. Okay, so so that's about that. And then you can try this problem and see whether you get the answer. And then so this is a practice problem. You can try this. So the exercise, use the fourth order, that's what called for the fourth order, use the fourth order Runge-Kutta method, use the fourth order Runge-Kutta method to approximate y1 for let's say y prime equal y minus t squared plus 1, where t is in between 0 and 1, and y0 equal 0.5 with let's say h equal 0.2, because we don't want to do too much. Even with 0.2 you have to do 5 calculations. Okay, and so you can see the answer. You should get something close to y1, which is approximately equals to 2.640827. Good. So as the last thing that we discussed, so what we actually use in softwares to calculate numerical solution. So there's one that we call the adaptive methods. So let's talk about that. So I'm going to give you this as a note. Adaptive methods. Adaptive method. So one of the problem that we have in a situation is, so we can see that we use the same h. So using the same h is not really the best thing that we can do. So for example, let's look at this graph. So if you look at this graph, so let's say you have a graph like that. Okay, so if you have a graph like that, and you can see in certain places this equation is the curve is like almost linear. When you have equation almost linear, we don't need that many intervals. So for here we can use less number of intervals, because this is like looks like almost linear. But when it curved, we try to use more intervals. So for here we can use more intervals, and then again less intervals, and again more intervals. So that's the so what we can do, we're gonna change the gap and then less, so like that. So when they are more curved, we can use more intervals, small h. Okay, when curved we use smaller gap. When it is linear, so it's like almost looks like a line, we use large gap. So this is what we call the adaptive techniques. So we're going to kind of change the h value depending on the curve, but this going to make calculation much accurate. So yeah, so let's talk about that. So we're going to use different step size. Depending on the function behavior. Different step size depending on the function behavior. Okay? Function behavior, that means when they are more curved, we use more subintervals or less h, small h. When this almost looks like linear, we use few subintervals. This method is called the Runge-Kutta method. Runge-Kutta Runge-Kutta method. Method. So this can use in the calculation. This can use two Runge-Kutta methods of two orders. Use two method of order 4 and 5 because they need to use they need to first calculate what are those gaps, and then they use, depending on the gaps, they use two different ones. So they use order 4 and 5. So because of that, so this one named as Runge-Kutta 4-5 in MATLAB. In MATLAB, we call this ODE 45. But that's the Runge-Kutta order 4-5 method. Okay, this is very, very accurate, and you're gonna get excellent results. Good. So this is the end of the numerical techniques discussion.